Hello everyone, this is Somashekar Aditya. I am from NITAB and I am here to explain about golden selection search and which optimizes a function, and this is mentored by Polikishore sir. And first of all, let's get into the introduction. What is meant by golden section search and why we use that and how we use that, all of those. Okay, coming to golden section search, yeah, it is a numerical optimization algorithm. Yeah, if we take a complex function, then we need to find a maximum or a minimum of a function. We will be having, it's a difficult task for us for a complex function to find whether it's a minimum function, to find whether minimum or maximum of that function. So to find minimum or maximum of a function, we use this algorithm, and this algorithm is only used for unimodular functions, which means it has only one minimum and one maximum within the given interval of time. So it means that if we take other functions, they won't be having any other two or three maximums in a particular given interval of time. If we take a particular function x square plus 1 like that, if we take an interval between 1 to 5, it is a unimodular function as such that it is only having one minimum and one maximum in the given interval which we have taken. So let's see what is meant by golden section search. It is a numerical optimization algorithm which is used to find maximum or minimum of a unimodular function within a given interval of time. Now how it works. So it takes 2 points from left side and right side of the given interval, such that it iterates, it removes uh, parts of certain region, such that from that removed region we can easily find out uh, what's the minimum or maximum of a function. So the method involves iteratively dividing the interval into two sections in a specific ratio known as golden ratio. Yeah, this golden ratio is found through, it is given as 1.618, and it is constant. This golden ratio is constant, and the section that has the smallest value of the function is retained, and the process is repeated several times. We'll be taking a tolerance value, and we'll be iterating up to our interval gets less than that of the tolerance value, such that we'll be stopping the iterations up to there. Then after that, we'll be getting an interval between those 2 points. We'll be getting our maximum or minimum of a function. So how this golden ratio is found? It is the adjacent ratio of two Fibonacci numbers, such that the ratio between them is taken constant as it goes on. We'll be taking it as a constant. Then we'll be finding the golden ratio. Well, uh, coming to golden ratio, the golden ratio is denoted by grid phi, and this is a constant fascinating mathematicians and artists and architectures for the centuries. It is defined as the ratio of two quantities, such as the ratio of the both larger quantity to the smaller quantities equals to the ratio of sum of the quantities. Yeah, as we discussed earlier, we'll be taking that ratio as fixed, such that as we'll be taking large numbers on upper side, so adding a smaller value to the numerator does not affect to it. So we'll be taking a plus b by a equals to a by b, such that we'll be finding the value of phi, and that we'll be getting as root 5 plus 1 by 2. So that is only known as, we'll be getting two values for that: root 5 minus 1 by 2, root 5 plus 1 by 2. So root 5 minus 1 by 2 is 0.618, and root 5 plus 1 by 2 is 1.618. Yeah, like this we'll be doing. Yeah, we'll be taking x1 equals to a plus d, and where d equals to golden ratio multiplied by interval length, and x2 equals to same b minus d, as we'll be taking the points within the interval. For a we'll be taking up to distance from here to here, and for b we'll be taking up to distance from here to here. So we'll be getting 2 points in between our interval, and where D is the GR into interval length, where GR is the golden ratio and B minus A is the interval length. And coming to the algorithm means how it works, how we'll be doing all this. So here golden section search algorithm is a method to finding the minimum maximum of the function the given interval of time, as we discussed earlier. So at starting we'll be choosing 2 points here and here, and after this is A and B are our given intervals, and C and D are our x1 and x2 points. Let's assume x1 equals to C and x2 equals to D. So here we'll be choosing two initial points A and B such that interval A and B contains the minimum or maximum of the point. So we'll be calculating C and D such that C equals to A plus D and D equals to B minus D, where we know that as we discussed earlier, what is D? Uh, D equals to golden ratio into B by A. Their golden ratio is here, yeah, we taken as 0 root 5 minus 1 by 2. Here we'll be taking 5 equals to 1.618. There we have taken 0.618, and here we'll be taking 1.618. So to get our points in between them, we'll be dividing interval by a golden ratio such that we'll be getting D. That is the length between A and C. So after getting C and D, we'll be evaluating the two functions f of C and f of D. So we'll be finding functions f of C and f of D. We'll be evaluating the two intermediate points C and D, and we need to find the values of C and D. After that, if f of x1 is less than f of x2, which means f of C is less than f of D, then the minimum or maximum point must be lie in the interval a comma x2. So we'll be if D is greater then f of D is greater than f of C, then we'll be removing this whole region, because uh, above this all we'll be getting maximum points. So up to here we'll be taking as a new interval, then we'll be doing iterations. So after that we'll be removing this area, and we'll be taking new interval as a comma D. So here it's taken as a comma x2 up to here and here, as we assume x2 equals to D. So only this up to here and here interval is taken, and again we'll be finding new C and D, new x1 and x2, which means new x1 and x2, and iteratively we'll be doing that. If f of x1 is greater than f of x2, then minimum and maximum of the functions. So if f of C is greater than f of D, then this region will be going off, and our new interval will be is C comma B. So from here we'll be finding new x1 and x2, which means new C dash and new D dash. Then after we'll be doing the same process which we have done earlier. Again we'll be finding f of C and f of D, and if again we'll be checking f of x1 is f of C is greater than f of D. If that is minimum, again this area will be going, or if f of C is greater than f of D, then this area will be going, and we'll be finding new points up to which we'll be taking a tolerance value, up to which our interval value is less than our tolerance value. We'll be finding iterations up to there. After that point we'll be getting a value which will be taken as this point plus this point by 2. We'll be taking the median of that interval, such that we'll be getting the minimum point. For that minimum point we'll be getting the minimum value if we want. If we have done for maximum, that optimum point, if we substitute in the function, we'll be getting the maximum value in that particular interval. So as we discussed earlier, we'll be repeating the steps up to 2 to 5 if it is a general practical case, we'll be will be stopping up to 2 to 5, but when it is coming to implementation, then we need to, it may be going up to 30 iterations, 40 iterations, depending upon our tolerance value. If we have taken tolerance value to e minus 7, then we need 1 e minus 7 or 2 e minus 7, which means that we'll be uh, we'll be finding the values very precisely. We'll be finding the values very precisely, as 1 e minus 7, which will be equals to 10 power minus 7. So we'll be iterating as such as our interval reduces very narrowly up, such that interval gap is also equals to into up to power 10 power 7. So then after, as we discussed, the minimum or maximum point is at the midpoint of the final interval. Yeah, at last we'll be getting a some interval. So then how to know which point is minimum and how, what to take as minimum point or what to take as maximum point? We'll be taking the midpoint of that interval, a median of that interval. If we take, for example, if we take 1 comma 2, if that is a final interval. No, it is not, but let us assume that it is a final interval. Then the optimized point is 1 plus 2 by 2, that is 3 by 2 in 1.5. Like that, after we will getting the final interval, we will be choosing the midpoint of that interval such that it is our optimized point. Okay, and this notice that we'll be using this algorithm only if it is an unimodular function which has only one minimum or one maximum point in our given interval, in which we'll be taking. So for this, let's get into the code and how it works, in how it, it gets worked or it gets implemented in Python. So to run this, at starting we need to import some libraries from Python such as math and numpy. As we know, it takes all inputs in arrays and matrices. And this matplotlib, which is used to to plot the graph, and this is to clear our output in the which will be used in the plotting the graph. And this time library used to have a gap between our intervals when it is showed in our graph. Let's get into, as we know, as we discussed earlier, we have taken golden ratio root 5 minus 1 by 2, which is equals to 0.618. So coming to this, we'll be taking a function here, a function f of x comma x. So here we'll be defining a function. So if we call this function, we'll be getting this x square plus 2x plus 1. If let's assume that this is a function, and we will be calculating our value in the interval minus 2 comma 0. Yeah, import, as we saw earlier, numpy, matplotlib, ipython display time, these are the libraries which we will be importing in our code. And as we know, r equals to root 5 minus 1 by 2, that is golden ratio, that's we have written here. Then after this part, this is where we'll be defining a function. uh, it may be x square plus 2x plus 1 or something else. If we take x square plus 2x plus 1, yeah, we can take any function we want, in which we need to find in a particular area x, and then in between our interval minus 2 comma 0, and what we thought of finding minimum of this function or maximum of this function in the particular interval. And coming to this area, here we'll be updating our interval, like we'll be taking some certain interval. uh, for this example, we'll be taking minus 2 comma 0 as our not general interval. So here xl is minus 2 and xu is 0. So for this particular problem, what we have chosen some particular interval. So to rand to generalize for every function, we'll be taking xl and xu. We have taken xl and xu, and we have discussed earlier. We'll be finding two interior points x1 and x2, which means x1 equals to xl plus d, x2 equals to xu minus d. As we saw earlier, there we have done that x1 equals to a plus d, x2 equals to b minus d. So here parameters are changing. Xl equals to a, xu equals to b. So that parameters we have taken. As we know that d equals to golden ratio into interval length. That changes for every interval. As interval changes, our d value is also changing, because for every iteration we'll be changing our we'll be we'll be getting a change in our interval length, such that some part of left side or right side will be cutting off. So for that we'll be having for a change in our d. Then after x1 and x2, we know those are two interior points which will they will also be fluctuating. As we call this update interior value function, our new x1 and x2 values will be updated. So we'll be having, as we discussed earlier, we can find minimum from this function, and we can find maximum for a function through this golden search section search. So let us discuss first how to find a maximum of a function. We'll be writing a function like we'll find maximum. This is a function we'll be writing in a Python for finding the maximum of a function x square plus 2x plus 1. So for finding maximum of a function, uh, we need to calculate our x1 values and x2 values. So here we'll be calculating our x1 and x2 values. As we discussed earlier, f of x, we'll be comparing our x1 and x2 values, f of x1 and f of x2. So now here we'll be checking if f of x1 is greater than f of x2, then right side part will be uh, cut off, and we'll be having update in our interval length. So xl equals to xl and xu equals to, we'll be getting a new interval length, as we can see here. So if f of x1 is greater than f of x2, so this region will be going off. If f of x1 is less than f of x2, this region will be going off, which means our new interval becomes a comma d, and this becomes our d dash, and we will be finding here c dash. This becomes new b dash, such that we'll be finding new c dash and new d dash. We'll be checking our new interval. So coming here, x if f of x2 is greater than f of x1, we saw, excuse me, here this case we are checking to this case. We'll be setting new b is equals to x2 and repeats from step 2. New b equals to x2. That's what we did here. New d equals to x1, and we'll be updating our interval. We'll be finding new x1 and new x2. Then we'll be getting an x optimum. Again we'll be going through this function. Else, if f of x2 is less than f of x1, xl equals to x2. So in the previous case, our xu value is changing. For now, if f of x1 is greater than f of x2, a value is shifted to c value, as we discussed earlier. If you can remember, a value is shifted to c value. So xl equals to x2, xu equals to xu. So again we'll be updating the new point and we'll be getting x optimum, and we'll be returning xl, xu and x optimum. To find the minimum of this function, same as maximum of the function, but here in the maximum of the function we'll removing the either side opposite of that, because to finding the maximum of the function it will be reverse of the minimum of the function. Maximum of the function can be found by two ways. If we have taken a certain interval, it can be taken. If we have taken some function f of x equals to x square plus 2x plus 1, if we need to find out that function maximum in a particular interval 1 comma 2, we can find minimum of the function which is reflective to x-axis of that function, minimum of reflective of f of x of the function with respect to x-axis. If we can find that g of x, let's take g of x equals to image of f of x with respect to x-axis. If we can find g of x minimum in the interval 1 comma 2, that minimum value of g of x will be the maximum value of f of x. Either in that way we can find, or in this way we can find maximum of the function. I prefer this way such that our basics will be good. To find the minimum of the function, again we will be following the same as that in maximum of the function, but this will be a bit clear than maximum of the function. If you get clear opinion on this minimum of the function, you can clearly understand what I explained, what we have discussed in this particular part, or in this particular function. So coming to minimum of the function, here we'll be finding f of x1 and f of x2, values of x1, function values of x1 and x2. So again we'll be having two cases. It may be f of x2 may be greater than x1, or f of x2 may be less than x1. So that we'll be using if and else loop, if and else conditions to check with f of x1 is greater. We'll be writing a new code. So if f of x2 is greater than f of x1, then our limit value changes to x2 and there will be no change in the upper value. So again we'll be updating the interior value, so such that we'll be getting new x1 and x2 values, and we'll be getting optimum solution as x1. And if f of x1 is less than f of x2 is less than f of x1, then we'll be leaving xl equals to xl, then again we'll be shifting xu equals to x1. So if f of x1 is greater than f of x2, so this part will be removing. That's what we are doing here. So that part is removed, and x2 equals to xu, x1 equals to new x0 and x2 equals to new x1, and we'll be taking x optimum equals to x1. As why we I mean what I explained is we'll be taking the midpoint, x optimum equals to midpoint of that interval. So why we are taking x optimum equals to x1? As the interval values are decreasing, we can take any value of that, any value of it. For a better value, I am taking this. If we take that also, it is normal general method. If we take here, we'll be getting a clear value. So if f of x2 is less than f of x1, xl equals to xl, xu equals to x1, we'll be updating here. Same as the above. So again, we'll be returning xl, xu and xopt. Uh, to run all these, we need to plot a graph. So this is the graph code. Here I am plotting sinus graph. Here I plotted x1 point. Here I plotted x2 point. Here plotted xl line, xu line, x1 line, x2 line. And this is y-axis limit. And this is our main function. So here it's starting, this it means iterations. This e1 equals to number of lines it took to. This is our tolerance value. Here, coming to here, this is our main point. We will be calculating, or we will be doing iterations up to which this xu minus xl value is greater than tolerance value. If xu minus xl value is less than tolerance value, at that point we'll be stopping our iterations, and at last we'll be getting our x optimum. Here x2, as we checked earlier, new x1 and x2 values are found. F of x1 is for getting find, and f of x2, and here this is to plot the graph. At starting we'll be not having anything on our graph, so it's starting just we are plotting the graph. If we given mode equals to maximum, means which means that we need to find minimum or maximum of the function. If we find, if we are willing to find a maximum of the function, we'll be typing max, or we'll be giving, if we are willing to find minimum of the function, we'll be typing minimum. So this will be our new. So if we are not in a dilemma to find minimum or maximum, it shows please define minimum or maximum of that particular mode. If we given maximum, maximum function will be running. If we given mode equals to minimum, minimum function will be running. And here this gives new boundary values, and iteration, I mean here when this code runs, this iteration value increases. This gives our how many iterations we are going through. This is our error value. Generally we'll be taking this as error, but for this we'll be omitting this time dot sleep, which gives our, this I'll explain you later why we took like this, why we have taken time dot sleep dot one here, which shows now, this shows our, this is used as this x equals to x axis and y equals to f of x in our graph. Here if we are calling our golden section function, golden section search function, golden search, this -2 is xl, this 0 is xu, and this is our mode, which mode we are willing to find. Let us take for function x square plus 2x plus 1. If we are taking my xl equals to -2, x equals to 0, and mode equals to minimum. So let us run this. So here we'll be getting, see, xl xu x, it's show, it's getting decreased. So if we take time equals to 5 seconds, we'll be getting 5 seconds delay. If again run this function, we'll see here. Here we'll be having this interval. After 5 seconds delay, we'll be getting a new interval such that this xl value shifted, this xl value shifted to this xu value shifted to here, and after again one iteration, xl value shifting here. This time dot sleep gives a 5 seconds gap between every iteration. For graph, it shows the graph, it changes the graph after every 5 seconds. This is the use of time dot sleep. So that is the use of that time library. We'll be having iterations up to here. So to get iterations little bit faster, we will be changing time value to 1. So here we will be getting our new iterations. So here we will be having a count how many iterations are going on. After completing total iterations, it gives us the final value, what is the optimum value, and how many iterations we have taken. So this gives us iteration value to so at at 35th iteration it got stopped, which means that our value of xu minus xl is less than tolerance value. At that point it got stopped and it's shown our -1 is our point, which is our x optimum point, and f of x is our, and 0 0.0 is our f of x, and this is our minimum value, and this is our minimum point or optimum point. So coming to results, so as we saw earlier, x square plus 2x plus 1 in interval, we will be getting -1, minimum optimum point as -1.00 at x equals to 0 comma 0. And what places we'll be using this golden section algorithm. This golden section algorithm is used in signal processing applications to find optimum filter coefficients that minimizes error or noise. Image processing also will be using this application to find noise reduction, feature attraction, and image segmentation. And we'll be using this golden section algorithm in optimum locations for wireless communications, uh, such as where minimum interface is going on, or where maximum coverage is occurred through minimum interface. And parameter estimation, the golden section algorithm can be used in parameter estimation also to find the problems, to find optimum values of the parameters that minimizes the error or model predictions of the actual data. And coming to conclusion, the golden section algorithm is a simple and efficient optimization that is widely used in various fields including engineering, finance, science, and more. Algorithm is based on the principle dividing the interval into two smaller intervals in a specific ratio, that is golden ratio, which ensures the algorithm converges quickly to up. Overall, the golden section algorithm is useful for solving optimization problems. Benchmark, and these are the references.